con 3:30 en punto. the International Conference on Electrical Engineering, Computer Science, and Automatic Control, CC 2025. I hope there are several speakers that contribute to very interesting papers this year. Unfortunately, due to the agenda, that are missing three of our speakers. We will start with the ID 201, titled A Reconfigurable Multi-View CNN for Breast Tumor Classification using intra and peritumoral region, presented by Dr. Wilfrido Gómez Flores and co-author Dr. Wagner Coelho and Alberto Pereira. Please.
Right. Thank you, Dr. Rafa. Good afternoon, everyone. My name is Wilfrido Gómez. I am researcher from Single Staff in Tamaulipas campus. And I'm going to present this paper with my co-author, my colleague Wagner Coelho from the Federal University of Rio de Janeiro. While we are working about several years ago, we started working with breast cancer machines. Okay. And now we are proposing some convolutional neural architectures for classifying breast tumors. Now this is our last approach. Well, this is a global picture about breast cancer in the world. Yeah. Here we have data from 2022. There are the latest data. These are from Globocan. Yeah. Here we can see the map or the world map about the incidence of breast cancer. And we can see that the more blue or darker blue is more incidence. Okay, the number is here per 100,000 people. And for instance, in Mexico, the incidence in 2022 was about 68 cases per 100,000 people. And now we can see here what happened. Okay, and here we can see the map about the mortality. It's more or less correlated. Okay, as can you see, it's more or less correlated. The larger the incidence, the higher the mortality. Okay, so in Mexico, the mortality is about 18 people. Unfortunately, they died about breast cancer. This is the statistics per 100,000 people. Okay, so at least in Mexico and several parts of the world, including Brazil, where I also work, breast cancer is a public health issue. Okay, some governments continuously are giving some programs to breast cancer prevention. Mexico is the October this month. Okay, to make a conscious in the population about this disease. So it's a big problem. To detect breast cancer, there are several approaches regarding the imaging modalities. We have these five are the main technologies for detecting breast cancer. We have mammography, that is a X-ray study. Okay, we have ultrasound, is a very high frequency wave sounds. We have magnetic resonance imaging, nuclear medicine like PIT. Okay, and histopathological images. Okay, these technologies are used depending on the stage of breast cancer or the necessity to detect a tumor. But for instance, the first one is the most used, okay, because it is cheap and we can use it in many people. Okay, ultrasound is a coadjuvant technology. Only as, for instance, in the mammography there is a tumor, but the radiologist is not very sure what is the composition of that tumor. He or she recommend an ultrasound, okay, to see inside the tumor what is the composition. Magnetic resonance imaging is most used when there is a positive detection of cancer, and is more used for screening before surgery of the tumor. Okay. In these three first cases, there exists a system to interpret the images. This system is called BIO2, or is the name of Breast Imaging Reporting and Data System. Okay, this system has two main things: has a lexicon to describe the image in general, and has categories. And these categories are the likelihood of malignancy. So, for instance, here is only a very tiny part of BIRADS, and it's BIRADS for masses. Okay. Here we have the BIRADS for masses in the case of mammography, because there exists for ultrasound and resonance magnetic imaging. In the case of BIRADS for masses, we have these three terms: shape, margin, and density. And as you can see, there are some descriptions about these tumors. So these are more probably to be benignant tumors, and here are malignant tumors. Yeah. So the idea is to standardize the reports about these images. So based in these features, these are subjective features, but based on these ideas, now we can use this to make a tumor classification, okay, based on that ideas. And there are two big approaches to make this: machine learning and nowadays deep learning. Okay, machine learning is about taking handcrafted features that we extract from the image. For instance, the shape. We can quantify the level of irregularity, yeah, intensity, also texture, and also we can include clinical data. Yeah, all these features create a vector, okay, that is the input to a classifier. And in our case, the idea is to classify that image in benign and malignant classes, two classes only. But we also can classify in many other classes. The difference with deep learning is that deep learning extracts automatically these features. Yeah, these features are learned by convolutional layers. Yeah? These convolutional layers are image filters that are adjusted to extract features that maybe we don't understand, but they are useful to make a classification of that. Okay. So these are the two big approaches now. And regarding this part, okay, deep learning, we can see that there are also another two approaches. Single view convolutional neural networks. This is the most common, in which we have only one input and we have one output here. Yeah, the network receives this image, make the convolutions, and perform the prediction at the last layers. In the case of multi-view learning, we have two or more views of in the case of the tumor. Okay, we have one image, and there is a branch of convolutions, and there is another branch, and in some parts, at different levels, we can merge these features, and at the final, make the classification. Okay. The advantages of using multi-view learning is that we can integrate complementary information. Yeah, because sometimes a single image do not have all the information that we need, and we can put here one type of information and here another type of information. Okay, but there are several challenges. This is the for me in this work the most important, the optimal biofusion. That is how to merge the features at different levels. How to do that? It's good at the final, it's good here, it's good to use tree. That is a question on how to make a configuration of this architecture. Okay, so this work deals with this problem. If we can see the state of the art, there are many works, but I only put three recent works that use this idea of making multi-view learning. For instance, that work, the first, is about liver cancer, and it uses two branches, okay, and a central network to make a fusion at different levels of abstractions of that features. There is another work similarly to that one that is for lung cancer, and it merges also the features and handcrafted features. Yeah. And this is another study that we made some months ago with a student, and we can combine two or more views of the tumor. Okay? But here the problem is if this architecture is good, okay, to improve the classification performance. So that is our problem statement. No? Multi-view CNN architectures are fixed, like in the state of the art. We cannot move. We only see that the architecture and see the results, but the question is it good? Okay, so we cannot evaluate the impact of merging the merging features at different depths of the level. So our proposed approach, we apply this to mammography and ultrasound images. Okay, all these data sets are publicly available. Yeah, for instance, this Bruce Brand is ours. We created this data set, but the others you can download from the internet. The number of images are more or less good. No, it's not too much for deep learning, but it is the number of images that we have. So 2037 for mammography and 2685 for ultrasound. Okay, and there is different numbers that also for benign and malignant classes. All of these images has been biopsy proven. That means that we know exactly if this tumor is benign or malignant. And also there is a segmentation mask that encloses the lesion to know where is in the image, and also encloses the shape. That is important for our work. So how we extracted the tumoral views? Here we have a mammography. Yeah. For instance, here in this tiny part, there is a tumor. Okay. And this tumor, we are interested in analyzing the intratumoral region and the peritumoral region. This will be our two views, what's happening inside and what's happening at the edge of the tumor. So when we apply this idea to our images, we can see these things. For instance, this is the standard way to make a region of interest. There is a non-masking. Only we have the tumor for mammography and the tumor in breast ultrasound. And these are the two views that we are evaluating: the intratumoral view, okay, and the peritumoral. The area of this surrounding part is almost equal to the area of the tumor, to have the same number of pixels. And also to avoid losing the aspect ratio of the tumors. For instance, when we are going to use a CNN, we have to reshape the image, yeah, to make the image generally a squared shape. So, for instance, if we this image or this tumor that is almost oval, if we make a reshape only without considering the aspect ratio, maybe if we stick in this dimension, it becomes round and loses the aspect ratio. This is important in tumors. So we made a padding to ensure the aspect ratio of the tumor, and also and once making the padding, we make the reshape. Okay, so this images has the same size, but with this kind of padding. And the blue part is only the masking that we extract from the segmented tumors. Okay, I mentioned that in our data set, we have the segmentation masks. These masks are used to extract this. Okay, and how is our proposal? In our nested network, the idea is to have two branches of neural networks, or in this case, ResNet 18. Okay, ResNet 18 is a convolutional neural network that it already exists. Okay, and we have this for intratumoral view. This is the input, okay? And the convolution is forward. Yeah, and here the input is the peritumoral view. And the idea is to test. No? In our program, we can reconfigure this CNN. At least we always have this part. This is the output part. Okay. We have here the last layer is the softmax, and we here we merge in this fusion block. We merge the information from these last 2 points, but also, and we call this with this code 0000 because all of these are off. Okay, but we can put this. Okay, we can reconfigure the neural network automatically in our code. We only say, I want to put turn on this and create this article, or I want to turn on this and make this. Okay, so we tested 5 configurations, okay, increasing the number of fusion blocks, and to respond the answer which of these configuration is good or is the best. Okay, not to make a fixed architecture, but evaluate the impact of the levels. And also we compare our work with these reference methods. See? First, we compare with single view signals, using the non-masked. This is the traditional way of making breast tumor classification. We put the region of interest without masking and perform classification. And also we tested every view independently, the intratumoral and the peritumoral. And here are 2 other approaches multi-view from the literature. And the architecture is almost like this. This is similar to this, but the change is in the blocks, in these fusion blocks. Yeah? In our case, there are these kind of fusion blocks. In this work, they use an addition at the first layer to merge the features, next convolution, and max pooling. And in the work of my student, he made concatenation, and this structure is like a ResNet structure, okay, that is inside of these green blocks. So, and the classification assessment, we use 5-fold cross-validation. Our data set was divided in 5 independent defaults, and one part is for test or for training, and the other part for test, until all defaults become a test set. Because the number of images are not too very big, we use artificial data augmentation to increase the number of training data, and we train the model. Yeah. This or any of these. Follow the same experimentation. Okay. With the model trained, we make the inference using the test set, and we measure the classification performance and made a statistical test. And the performance indices are these: sensitivity, specificity, the most common, the matrix correlation coefficient, which is good for class imbalance data. In our case, our data is unbalanced, so matrix correlation coefficient is better than accuracy to measure the classification performance. And the statistical test is the McNemar test. Yeah, this test we make with a confidence interval of 95%. And the idea, this is the null hypothesis. It says that method A and method B have the same error rate, or the alternative hypothesis, they don't have the same error rate. Okay. Well, the results are this. These are first evaluating the 5 configurations for mammography and ultrasound. Yeah. The idea is to see which configuration was the best. In the case of mammography, this configuration, only the last one off was the best. And here the p-value indicates if the other methods are statistically significantly different from this method. And in the case of mammography, all the configurations perform, there are no statistical differences. Okay? But if, for instance, this, which has this architecture, it has 24.63 million of parameters. If this performs as well as this is the simpler with 24.006, we prefer use this because it has less trainable parameters. Yeah. And statistically, they perform similar. The same case is with ultrasound. Yeah. Here, the best method was the most simple, but also there was only here was a statistical difference. In the other cases, no. So at least in this result, we can see that using a simple architecture, that means this is enough to make a good reclassification. Yeah. We don't need the others. And this is comparing with the reference methods. In this case, the method that we are proposing is 0000 was the best, but the statistical test indicated differences in the others. So we already improved the classification performance. At the final, this is only to see the explicability of the network. What happened when we are increasing the number of fusion blocks? For instance, this one was the best at the final. But we notice that when we include more levels of fusion, we can extract more finer features from the tumor contour. Okay. It's only to see why, for instance, the network, this image predicted it as benign. We can see at least what are the weights that the most relevant weights to make the decision. This method is GradCam, GradCam plus. Okay. And conclusions. The reconfigurable property allows us to determine which architecture is the best. Okay. We notice that a single fusion block is enough. We don't need the others. Like in the state of the art, there are many other fusion blocks. Why they work? Because they capture relevant and complementary information. We have the inner part and the outer part of the tumor, and we know that these parts are complementary. Each network learns different things, and at the final, the merging improves the classification performance. The same information is very important to obtain the classification performance improvement, because in the shape, we have the morphological information of the tumor that is very related to the malignancy. what is the limitation of this method? That we must need a segmented tumor, okay? And that segmentation must be reliable, okay? If we don't have a segmentation tumor, this method we cannot apply, okay? It's a limitation. And future work, ideas is to explore other fusion methods and also another networks. We use ResNet 18, but we can use another architectures. Some reference, this QR, if you are interested, I have here a GitHub with the codes to build these networks that I present in MATLAB. Okay, thank you.
Thank you, Dr. Will. Now we will go to the question that if you have any question to propose, please, this is the moment. Anyone? Okay, I would like to ask, sorry.
I have some questions, but I need to find them. For example, if I have a question, you said that you have a repository that you made. I would like to know how it was to get the images, or if you co-work with any institution, or how it was.
No, for instance, if I can, this is very popular for mammography, DDSM, okay? And there is an article in, if I don't remember, it's scientific reports, I think, or scientific data. Yes, there is an article where they made the report of that data set, and the data set is in the cancer archive, is the repository in the internet, cancer archive. And this, I asked to the authors, BCDR, I asked they are, Imbres are from Portugal, and BCDR, I think they are also from Portugal. But I asked to the authors of the data set, they sent me an agreement that I only use these images for research, and they released the data set for me. Postbra is our data set. It's also in a repository. We have an article also. And this you can download also from, for instance, Bosi is from Egypt. And there is also a repository. Udiat, I write to the authors, and they send me the images. Wasbook is a data set. It's different from the others because Wasbook is the signal, the RF signal of ultrasound, and I have an algorithm to reconstruct the image from the signal to the V mode image, and also it's free. If you are interested, I can send you the links to contact or to download these data sets.
I would like to also the thing. I saw this about multi-view, and I think it's my first time that I see something like that you can merge with different levels. And I want to ask if this is recently, like a recently idea from you, or if it's
no.
Like
Multi-view learning is it has many years that exist, and also here in my references, this is it's a good review of multimodal deep learning for biomedical data fusion. Makes a review of many methods. It's not from my idea, but we reuse some ideas that are in these papers. Yeah, but multi-view learning exists from the neural networks, traditional neural networks, and now deep learning. Here the challenge, I put here some challenges if you are interested in this research, is the construction of the good architecture, the model complexity, because, for instance, ResNet, our architecture, this network alone is 11 million of parameters. And we put another view is the double. And we want to put another that we also do that. Okay. So how to reduce the complexity but maintaining the classification performance? Yeah, that's another challenge. Also it's correlated because if the model is very complex, the train this is also very slow. Okay, we need a very good GPU. And also the viewing consistency, we need to ensure that if this tumor is one information of the same tumor, we have the complementary information in the other view. We cannot see different things. It has to be the same phenom with different extraction of data. I don't know how to say. Okay. So, but there are many others. It's a little bit difficult to work with this because the complexity, the model complexity.
And I have another question. I was thinking now about the reshape. If it's possible that, for example, if it's, I don't know, if the image took it like this, instead of making the reshape, is it possible to put, for example, black pixels here, so it doesn't change the shape, or is it better to reshape?
In the case of tumors, it's important to maintain the aspect ratio. The aspect ratio is the relation between width and height. For instance, this is an oval tumor, and this is the original image. Okay. If we make a reshape, to make this image, for instance, 224 by 224, that is the standard size of the inputs, we need to stick. But the shape becomes round now. So what I do, I cut the image, and the first thing I do is the largest part of the image I resize to 224 pixels, and the other side also sticks, but in the same proportion. Once I have this first resizing, I put this padding. I put in yellow as illustrative, but in real it's black because there are black pixels. I only put in yellow to better have a visualization of this. Okay, but in the reality they are black, and this blue part it is also black. But this is padding and this is masking with the tumor segmentation. Only to make a difference.
Okay. I thought that it was making the resize, but without the path. But now
Okay.
I
Yeah. The path is always black, or it's a single color. It could be black, white.
For example, I was thinking because I took a class about the image processing, and we so for example, when we make the gradient of the images, it gives you the contour. But for example, today I've seen a lot of presentation that they say they use binary segmentation, and I thought, and also I saw the other day that other persons were making like an autonomous, say, it was like a little ship,
Okay.
but it's putting like two angels so it can follow like a certain path. And they are well also using the binary segmentation. And I thought that it was similar to the gradient, and also it give you use the contour. So why is it used more the binary segmentation in these cases?
Okay. For instance, here, all of these that the does images, we have we have the grayscale image, and we have another one that is the binary image. In the binary image, only the white pixels are this tumor shape. Okay. I can use the contour depending on the application, but in this case, I need all the region, because when I multiply the binary image multiplied by the grayscale image, I only enhance the internal region. That's why I need all the internal region of the tumor. In the case of the contour, we can use the contour. For instance, we can calculate the contour of this binary and make a delay, a morphological delay, to make this like a donut, to have this. But this also is also a binary mask to produce this. So in reality, I use both the binary mask to produce this and the contour, but with the dilations, morphological dilations to produce this.
Okay,
Yeah.
like two types of segmentation.
Yeah, for instance, I calculate the contour. Yeah, it's only like a line. And next I perform is a sequential delay tones. I don't know if you have you seen ever morphological operators, morphological mathematics.
I have here like one
It's
more difference, but honestly I don't.
The dilation
I don't know.
operator is made more thick, and I made this several times until the area, this blue area, is equal to the area of the tumor. And the algorithm stops. I produce the mask and multiply by the grayscale image to obtain this. But in reality, I use both.
And for example, like right now we are analyzing just one in here, but can you imagine the neuronal network is also used to how to say with the convolution go and check where it is, and it's not only one. It is searching for how many it has, no? How many tumors it can have.
But inside the network, you say.
No, inside, for example, in this image, we see one. We are analyzing one, but it can have three tumors.
Yeah. In the same image. Yeah. But only we analyze a single one. Only a single one. And if there is, for instance, here another one, we analyze in another process. Yeah. But it is possible. We can detect all the tumors at the same time, but the analysis is one by one.
And for example, I had one question. Well, from what I understood, is that every level on a neuronal network, we are losing information. But how is it possible that when you show it us the images, well, my eyes it see more clear. It is more the shape. It's clear, more clearly. I don't know how to say more clear.
But in one case, for instance,
This
okay.
for me in
that
my eyes,
analysis, yeah.
I see it better. But from what I think is that every level in the network we lose information. But when I see it, for me it has more.
Okay, yeah, I understand. These images, she's talking about the GraphCam analysis. This, okay, you are right. At the final of the network, here, I took the feature maps here. No, here, here, and they are tiny. But we have here. I'm not wrong. Here there are 4,096 feature maps. I think. I don't, but there are a lot. Okay. And this method GraphCam makes to look for the maps that are more activated, but they are tiny. And the final process is to make a resample to make that tiny image to the same size of the original image. But this image that is overlaid is the sum of several activations. It's not a single one. From the 4,096, some of them are important. They are summed, precised, and overlaid over the image to see where are the most important parts to make that predictions. What can I see is that, for instance, for a malignant tumor, in the last configuration, that means if we use this, when we concentrate here all these features, yeah, we can extract very fine information from the edge. And in the first, okay, that means this, we can see a more global in that area of the image. But that's why you can see, but because there is a process, there is an algorithm. The name is GradCam plus plus. This is the reference. GradCam plus plus, and the GradCam is the gradient-based visual explanation. Yeah. We extract these feature maps that are the most relevant to make the prediction. This explicability, because neural networks are black boxes, and at least we can see what are the most important features to make a prediction.
And yeah, my last question. How can we get the artificial data
Artificial documentation. Okay, that's a simple, it's in the here. The first thing is artificial documentation is only applied on training data. Non-validation, non-test, only training data. The artificial documentation means that the image, I made some geometric transformations like rotation, scaling, translations, and also I made intensity variations. The bright I can make darker or brighter, and also I can pass a blue, like a blue, or some kind of filters. The purpose is to increase the data set with new images. The idea is to improve the generalization of the network with images that can be produced in the reality, but we don't have that images and we produce artificially. And the transformations in that part are random. I have a range to pick some value and make the transformation on the image. And also another advantage of artificial documentation is that we can balance the number of images. For instance, I can increase the malignant set to become more or less the same as the benign, because in classifiers, imbalance is a very big problem, because the classifier learns the majority class. That's the advantage.
Thank you, Wade. Just
Okay.
question, please.
Do we have time?
Of course.
No
Okay.
se ha conectado.
Okay. Just as a matter of curiosity, how much is the improvement with the multi-view learning in comparison with the single one? Or did you
Okay.
try that?
Yeah, is this that?
I missed that part.
Because it was quick.
Okay.
It's here. Okay, these three. Okay, this is single view, SV,
Okay.
and multi-view. So single view with a non-masked image. What is this approach? Is the traditional approach where I have a convolutional neural network and they put this only the image as is.
Yes.
Okay, and the other two is introducing the intratumoral region and the peritumoral region.
But did you try including the peritumoral region in the non-mass?
Yeah, here is also see?
Both together. Okay, great.
Yeah. It's also right. So the improvement, I like this index, MCC, is like accuracy, but this is more balanced for class imbalance. It's because accuracy is tricky. You can have a 90% of accuracy, but it is because the 90% of one class was exactly the other class. Okay. MCC is better. So in our approach, it was the simple one. It was 71 of MCC. And for instance, the original is 0.58. We tend to unity to be best. And also the statistical test, they said, oh, look, the p-value very low. There is no chance to have the good or the same performance by chance or by random. Okay. And the other, these are two multi-view. And also the improvement is better than the others, but ours is better at the final. This configuration. This configuration is the most simple list.
Okay. Super interesting. Thank you very much.
Thank you very much. I would like to propose one last question. As I understood, the objective was to do a segmentation of the tumor, right? But which in the conclusion, you also mentioned that it's important to take account about the geometry shape or the shape of the tumor. If I'm not mistaken, you used only lateral oblique images, right?
In the mammographies, they are both cranial and lateral.
That's right, because sometimes in the craniocaudal view, the tumor may seem different because the point of view is different. So maybe you can have some skew aspect of the tumor.
Yeah. In reality, all the images, depending on the data set, but all the images has to be used. The craniocaudal, this is lateral, oblique. And in both images, we have the segmentation.
They call the standard images.
Yeah. And we treat it as independent images.
Right.
Yeah. But you're right, there are some approaches where the multi-view is one is from craniocaudal and the other is from
separate.
Yeah.
Okay.
That's a good idea that we can, I think, to implement in the future. Use peritumoral 4 views.
Actually, I told you that it was just only one view, and then you will do the next.
Yeah, but 4 views, but it is very. The training of this architecture is heavy, very, very heavy. You can download this in this. I have here two architectures. You can reproduce this one.
Yeah.
Is from my student, this architecture, and you can reproduce the one I propose. But in both cases, you can merge, you can move the number of views. I put 2, but I can put 3, I can put 4, and automatically it creates the network.
Okay.
Yeah. So this is free to use.
Thank you very much.
Okay.
We will continue with our agenda. Okay, on behalf of the two speakers are meeting, we will continue with the next one. ID 195, multi-class hand image dataset for segmentating and preparing functional zones, presented by Fausto Cortés, Cuauhtémoc Sartí Rivera, and Wilfredo Gómez. Please, Fausto.
Thank you. Hi to everyone. Good afternoon. Thank you, Dr. Bye. So, as the doctor said, I will present to you this work that actually is about some hand images and AI. And I'm going to start. The work is called Multi-Class Hand Image Dataset for Segmenting and Inferring Functional Zones. My name is Fausto Cortés. So I'm going to start here talking about why hand segmentation matters. Well, this is a task that is relevant. This is a core task in some areas such as prosthetics, human and computer interactions, rehabilitation, and finally, it could be in virtual and augmented reality. However, some of the existing datasets with hands are too limited, they are too basic. Mostly, the majority of the datasets only separate the hand from the background, as you can see in this example, or they are coarse. So they don't provide any functional data, they don't provide any contextual data about how the images were taken. And so our goal was to provide an acquisition protocol to construct to make a dataset with hands and adding functional data and some anatomical annotations for this dataset. So in order to construct this dataset, we make this acquisition protocol. We are going to try to achieve 1,000 images. This is a very hard task. So we are trying to make just one hand per image. We are considering two general views. We call them palmar and dorsal view, as you can see in these samples. We are considering two exercises or actions. We call them pinch grip or fully extended hand. And we are considering also the illumination conditions. All the images were taken in these both conditions, natural or artificial. And there are a lot of variety of backgrounds between paper, wood, walls, desk, etc. And the minimal resolution for our images was about 640 by 580 pixels. After the acquisition of the images, we manually labeled all the images using the MATLAB image labeler tool, as you can see in this animation. We made 13 classes. 12 of them are anatomical classes, as you can see in the table. The palm, the thumb palmar, index palmar, etc. All of them has their own ID and label and a color. So you can see here some examples of the general views. This is the palmar view, and this is the dorsal view. As you can see, all the fingers has their own color, and this is actually 4 examples of our labels. This is the structure of our complete metadata that we are recording with all the images. We are recording the exercise, what type of exercise, if it's the extension of the grasp or the grasp. The hand side could be left or right. The view, if the hand is holding an object. The skin tone, we are proposing a scale from 1 to 10 for this skin tone. And finally, the illumination conditions. Before we train our model or general model, we went through a quality control where we eliminated the duplicated and corrupted images. Also, we resized both the images and the masks. And finally, we make a consistency check where we are trying to validate that every mask, every ID in the mask corresponds to the original images. After we labeled all the images, we can see here in this. Okay. As you can see, the pixel distribution in this graph, we can see that the palm and the dorsal regions are bigger than the others. The doctor talked about the imbalance of the classes when we are trying to work with these networks. We have to correct this. So to correct our pixel distribution, we use a class-weighted cross entropy loss, where every weight is simply the inverse of its frequency, or in other words, is the count of all the pixels, and then we normalize these weights. And with this, we can correct this problem. So after that, we prove this method, training a simple model using the DeepLab V3 Plus. This is CNN that is specialized in semantic segmentation, and we use a ResNet 15 as a backbone. We replace the pixel classification layer with the weighted class, and what else? We also made an augmentation with horizontal flips, and that's all the important slide. This diagram illustrates the network. Here you can see that the DeepLab V3 Plus has two main parts, the encoder and the decoder. The encoder is where the ResNet 15 extracts the deep features, and then the Atrus spatial array pooling captures multi-scale information in order to, after that, combines the decoder with low-level feature maps to recover the boundaries and the edges. And finally, we have the output, that is the mask that we are trying to achieve. Here we can see, we can summarize the metadata. We can see that we have more grasping exercises than the extended ones. We can see that we have a lot of left hands more than the right hands. And this is not in my conclusions, but I think this is because of we are trying to make photos with our right hand, and for this reason, we have more pictures of left hands. Also, we have more artificial illumination conditions, and this is also important. We are, as Mexicans, we have skin tone darker than the median. So here we can see the training performance of our model. We can see that the training is reaching almost about 95%. And then the loss plateau almost about the 40 epochs. We can see that we use the class-weighted cross entropy, and this helps us to stabilize the convergence of our model. We cannot see a clear overfitting indications in this model, so this is aligned with the training and validation that we obtained. And to make a quantitative evaluation of the model performance, we try to make an internal evaluation with 100 images. You can see here the performance with the global metrics. We obtain an overall pixel accuracy about 94%. The mean Jacquard index is about 62%. The mean also the dice index is about 75%. And as you can see in this table, the region of the palm achieves the best scores, about 96% for the index, the Jacquard index, and 97% for the dice index. And also, as you can see, the fingers, the little fingers, or the smaller regions of the fingers continues or remains as a challenging task. Here you can see the normalized confusion matrix. We can see a strong diagonal. You can see that the palm is about 96.5%. This is the best score we have. Also, we have an optimal result for dorsal and two palm. And we can see the misclassifications because these areas, these are small areas, or in some pictures, these fingers are frozen in the picture, so it's difficult for the model to identify them and separate or segment them correctly. This is another result where you can see this is more a quantitative more than quantitative result, because we don't have any mask of reference. We don't have ground truth from this data set. This is a data set called 11K hands. And you can see that our model makes, I'm going to say good or optimal segmentation more for palms, for example, here in this example, or the dorsal. And this is because maybe it could be obvious, but these are the bigger areas in the images. So it's easier for our model to identify them. So I'm gonna say the main outcomes for this work. We use the deep lab with the ResNet 15, this converged stably with class-weighted cross-entropy. We reach about 95% during the training accuracy, and the overall pixel accuracy is 94%. The index, the Jacar index is about 62%. The dice index, the mean dice index is about 75%. And as you can see in almost all the results, the Palm region has the best result with an index Jacar about 96%. And we have this clear misclassification concentrated in adjacent fingers that are the index finger and the middle finger, and the ring and the little finger. Also, well, the next steps or the future work, we are trying to add in more background poses, skin tones, etc. We are trying to make more pictures of this data set. We are trying to balance this work, so we need to work with another architectures and with other algorithms to try to balance this data set. And the model for in this moment is effective for coarse hand segmentation with high-level pixel accuracy. We are trying to improve the manually labeled mask. So we have to improve the task of labeling in a fine-grained finger regions. We tested our model in the 11K hands dataset. So we can solve in the last slide that the structure is preserved. And the original goal to achieve 1,000 images was reduced after the preprocessing and strict quality control. So we, at the end of this work, we just achieved 792 images. And I think that's it. If you have any questions.
Thank you very much, Doctor. Let's go ahead with the question stage. If anyone has a question.
Fausto,
Yes.
can you talk about the loss function that you use?
Yeah. This is I don't know if this I have a lot of images. I think this is a simple, very simple function where we are trying to give more weight to the pixels that have less representation in the problem. So as you can see, the fingers represents at least 7% each, or less than 7% each. So that this function is just to make the model puts more weight in the regions that are smaller than the bigger. So for now, it's simple, but this is the first. I don't know if this is the first steps for the model. So we think that we can improve this method.
Maybe in the future we can use dice coefficient as loss function.
Okay, I'm gonna try with the dice function. Thank you.
Another question? I'd like to propose a question. I think it's a very interesting study. However, how do you think about future application?
Yeah, as I said, I think this have a lot of potential applications. Maybe you can use these regions these anatomical regions, or maybe make what's the name of these globes where you can sense and try to give a feedback. Haptic. Yeah, you can use it, for example, for haptic applications, where or maybe to virtual and augmented reality, you can improve the applications that nowadays you can see or use in these areas, in these fields. So I think it has a lot of potential applications.
If any free time tomorrow, approximately at this hour, my students will also present a study, but where we make a glove for Mexican language science. However, still we are making or developing the hardware, right, in electronic, digital, and analog electronics. However, I think there is a very big potential with your study that we don't need anymore a glove that may be trained in terms of electrical signals and also accelerometer movements and another kind of technologies, just from the camera. A camera that would perform a segmentation in different regions of the hand in such way that the hypothesis should be that different regions that are segmented should map to a word or to a letter.
Yeah,
no?
That's the point. Yeah, or it could be not the substitute of that work or the hardware, but it could be like an additional help to your work, to your algorithm. So
maybe because a very heavy discussion we have in our studies that who in the real world wear a glove that it contains a lot of cables and all the microprocessors and a computer and all this technology that you have to wear in order just to communicate just a very few words, a very few letters.
Yeah.
Right?
that's it.
So I think that your study has potential to improve these findings and just to make by the side maybe this kind of hardware that maybe it's not that much necessary.
Yeah, I hope so.
Because nobody wants to wear a glove with a lot of cables. Okay.
Maybe with those glasses that just has a camera.
I
Yeah.
agree.
So any question, any additional question? No? Thank you very much, Pastor.
Thank you.
I must ask the rest of the authors have to communicate. No? Okay, so I must conclude this session, BIO2, titled Biomedical Engineering and Biomimetics. That belongs to the CC edition 2025 in the name of the organization and myself, Chairman Dr. Bayare. I wish you a good day.
Thank you.